send him the solutions, okay, for chapter 6. And you can check yourself. This is a good way. This is the one time I wouldn't go against using the solution manual. I hate the solution manual otherwise, but here I'd say it's okay. There's some numbers there. Okay. I don't know whether we can trust all those numbers. Didn't we have some trouble?
There's
Yeah.
some of them are
Yeah, there's some questions sometimes, you know. Be careful. I remember once in the solution manual, it was a methane as a fluid, and the author assumed, wrongly, the author is quite right. He just put the wrong number. He put 28 for the molecular weight instead of 16. Yeah. And of course, in his mind as he was working it, he was using the properties of methane, but imagining it was nitrogen. So be careful, okay? When you see something like 28, don't go and say, "Oh my goodness, that you've done something wrong." Question. Okay? This can happen. Any questions? Okay. And Chase would meet you in the student center.
Yeah.
Okay. At about 11:45 thereabouts. Okay. But I really want to make sure you get this. Okay. Thank you. What time do you? Good. I just want to point out one thing. Just one small thing, and so it's reason here. A few more minutes of your time. There is the last time I met, I pointed out that there's this principle called the principle of corresponding states. Principle of corresponding states. I want to tell you how you use it, okay? To use the principle of corresponding states, you will have to appeal to a chart, okay? The chart's fairly straightforward to use for most of it, but I want to point out to you how you do this. When you use corresponding states, and I derived this the last time, but I want to tell you how you're going to practically use it to calculate delta H's, for example, and delta S's, for example. You need to first know the fluid. I know. You say, what's the whole deal of using corresponding states? If it's scaled, isn't it true for all fluids? Mostly so. It is, in some sense, it is scaled. But you do need something. You need the critical properties, TC, PC, and VC. These are given at the back of a book or in a handbook or internet, or in the case of an exam, I give it to you. Okay, I'm the handbook. Now, you're going from point 1 to point 2. Let's get this straight. I have a PT diagram. I'm going from 1, okay, P1, T1 to P2, T2. I'm going down like this, and like that. Okay, that's the path I'm taking. In order to calculate the differences, say, in the H's. Okay? Let's pretend that's what you want for the time being. What you will do is, you will say, the difference, the way you're going to do this is calculate this difference, and then you're going to calculate that difference, and then go vertically up. So you're going to calculate H at P1 and T1 minus H down here, which is taken to be ideal. This is the ideal gas state. Ideal, okay? The same T1, and then you want to take H ideal of T1 minus H ideal of T2, and we'll tell you that's fairly straightforward, and then plus H ideal at P2 and T2. Now going back, I'm going in a certain path. You have to draw your arrows, otherwise you'll get confused on who you're subtracting. Yeah?
Is it T2 minus HT2, H ideal T2 minus H ideal T1?
No. I'm going from here to there.
Right. So do you final minus initial or initial minus final?
How did I do it? You bet. Sorry, that was the final
That one
minus
first,
initial.
right.
This is final minus initial. That's final minus initial. Sorry. That is not a
T2,
good.
P2 minus.
No. This is the first one, initial minus final. That's a final minus initial.
No, the first one's initial minus final.
Yeah. Which one do you want it to be?
Yeah, that's initial minus final. Let me put initial minus final.
Okay.
I was doing it right. Okay.
You had it
Initial
all
minus
the way,
final, initial minus final, okay, and now initial minus final. Okay, this is P1, P2, this is ideal, minus final. Okay, and where am I? P2, T2. So, this middle one out here, I'll put an arrow like this. That guy is the integral of Cp star dt, okay, of this one, T1 minus T2, okay? That's right, okay? That's T1 minus T2, okay? So you can see that this cancels this cancels this, and I get HP1T1 minus HP2T2, okay? This whole thing is the H in the first state minus H in the second state. If you want it the other way, just multiply by minus. Okay? Now, that's the middle one. This is what you're trying to compute. So I want to compute the first and the last using corresponding states. And what corresponding states does is it gives you a master curve. What corresponding states is it gives a master corresponding states gives a master curve, a master chart for, I believe it's H minus HIG divided by TC. If it's the other way, flip the sign, okay? That's what you have. This is what you have versus P divided by PC, which is also known as PR, P reduced. Okay? So what you do is this. Go to your chart. The steps are very clear. 1, find PR1. What is that? It's equal to P1 divided by PC. TR1. It's equal to T1 divided by TC. Go to the chart, read out H minus HIG divided by TC. And that is equal to term 1. This is what I call term 1. This is what I call term 2. And this is what I call term 3. So term 1 is this divided by TC. So if I want term 1, I multiply the number that I get times TC, and I get term 1. Okay? I do the same thing for term 3. 2, find PR2. PR2. Read out H, what do we have here? HIG minus H, just flip it, divide by TC. So all you have to know is to read the chart. If the chart's given as H minus HIG, you need HIG minus H, flip it, man, that's all you do, okay? Okay, and you get it, and that will lead to term 3. And you're done, okay? It's very straightforward. Now, if you're trying to read entropies, there's a second chart. And the second chart is much like the first chart, except it's not H minus HIG by TC. It is not S minus SIG by TC. It's just S minus SIG versus PR for a set of curves of constant PR. It looks like a much simpler to look at Mollier diagram. It's not as complicated and infested with lines everywhere. It's much, much easier to use because you only have a y-axis versus an x-axis for a family of z's, okay? And the z here is tr, okay? So there are some problems that have been assigned with the same thing. Try them out. It's just a question of looking at the chart, okay? It's kind of interesting to compare what you get from corresponding states, which is pretty approximate, with what you have in Peng Robinson, but it's not too bad, because you might wonder how they do it. I mean, the corresponding states itself must be using some equation of state, okay? It does. It's using PV equals ZRT. Well, there must be something for Z, the compressibility factor, right? Okay, so in some sense, there is a hidden equation of state in it. It's not like it's completely random, okay? And it's certainly not empirical. Okay? That is not. Okay? So I hope you can try these problems out. This is almost the end. We'll be working just more and more with these problems. So I'll meet you next Tuesday and Thursday, and we'll just work out some more of this.
I gotta go to work. Till about 5.
Okay.
Oh, there's some people who